So, good morning, Harish or Ravi Varman.
Good morning, sir.
Good morning. My screen is visible?
Yes, sir.
Okay.
Even audio is also clear.
Yeah. We'll wait. I mean, once you say.
Okay. Right, sir. I think it's the time to start.
Yeah, I'm ready.
Yes, sir. Good morning, everyone. I welcome all the participants once again for the last day of the FDP. I'll start with the introduction of today's speaker, our beloved professor, Dr. Harish Shankar Jain. Dr. Jain sir has received his UG from Jivaji University Gwalior and PhD from IIT Bombay. He worked in R&D department BHEL from 1974 to 2012, during which he was actively involved in completion of research projects and also published several patents. Post his retirement, he has been with Department of EEE, Vardhaman College of Engineering. Even in Vardhaman, Jain sir has established a research laboratory in which various prototypes are developed. Also, he provides consultancy for various industries. With this brief introduction, I would like to invite Dr. Jain sir to start the presentation. Over to you, sir.
Thank you, Harish. And a very warm welcome to all the participants. A very warm good morning to every one of you. Today, can we go back to my slides? The screen can be changed to my slides? Yeah, here. Right?
Yes, sir, it's visible.
It's visible to everyone?
Yes, sir.
Okay, fine. So today, let me first thank Harish for introducing myself, right? And let me share with you some of my thoughts on this topic, which is titled as Role of Power Electronics in Energy Efficiency. Most of you are fortunate to have born in late 20th century, but those of us who were there in mid of 20th century, we had seen electricity in its very naive form. Energy being supplied to you from a distant station located thousands of kilometers away from the utilization point, either in Himalayas or on the dams, maybe some thermal power plants far away from you. And the only means of transferring energy from these central power stations to the location or utilization point used to be transmission lines. The systems were primitive and there was no power electronics available till 1957. Let me be very frank. We used to work with old mercury arc rectifiers, vacuum tube diodes. So the use of electronics was also very primitive stage. This is where we started. Lot of inventions have been done by scientists, but because of a medium, and I call it power electronics, it was not possible for us to utilize energy, or specifically electrical energy, in its most efficient form. As time progressed, and we will see in this particular lecture, I would try to cover most of the things and try to bring to you the role of power electronics in improving energy efficiency, or bringing energy efficiency to its best. So with this small brief introduction, let me go to the first slide, where I would just like to give you a small brief or overview of the organization of this particular lecture. And as we go, we will be discussing objectives of energy efficiency, wherein we will say why energy efficiency is important and what are the objectives can be met with energy efficiency. The second section will deal upon developments in power semiconductor devices, that how much we have traveled from 1957 till date, and what are the options available to most of electronics or power semiconductor device based scholars for use. Then we'll go to the real part, where power electronics based applications for generation, transmission and utilizations we'll discuss. Few samples of them. We don't have too much of time to discuss every application. So we'll definitely take up some promising applications which have definitely made a visible change in our day-to-day life, and they have improved the energy efficiency. We will also discuss in later part of this particular lecture what next could be done by we electrical and electronics engineers to meet the future requirements and solve trending issues. Before concluding, we'll summarize, or in conclusion, we'll summarize what exactly is the impact and how it can be further improved. Of course, we'll have a question and answer session at the end of this, a long question and answer session. In between, I would like to break for a minute or two after every section, so that in case any immediate queries come to your mind, you can switch on your mic and talk to us. I will be happy if you can put it on question and answer panel or in chat panel. Maybe if not now, later I'll be answering them to your satisfaction. Clear? So the basic object
Not
of
yet, sir.
energy efficiency, as we know, efficiency is nothing but output plus losses is the total input, and the ratio of output to input is efficiency in general terms, and same thing is true for energy efficiency as well. Whatever energy is available to you and how much energy we are able to utilize or build makes the sense when it comes to commercial part of it. But if you talk in terms of technical units, It is how best we apply energy for our utilities. When we discuss examples, we definitely talk about it. The energy efficiency in turn provides us many things. And the main three things which we are looking for is energy sufficiency. What we mean by energy sufficiency is we have the resource available, energy resource available to us at an optimal cost 24/7 without any interruption. For a poor efficiency system, this objective is not met. Either you will have more resources with poor efficiency, or you will have loss of energy availability. That means you will have power shutdowns, you will have interruptions, so on and so forth. Even poor quality of energy could be, which is not provided to you or a consumer unless energy efficiency is looked into. Second thing is energy delivery. You can have a lot of resources, you can have sufficient energy, but because your operating expenses are very high, your tariff or the cost per unit of energy utilized is very high, which is definitely not liked by anyone or any user. And here again, energy efficiency comes and plays a vital role because it makes energy available to you, to consumer at an affordable tariff. The third thing is, and very important thing, is the environmental health. For making energy available to masses in abundance and at some cost, we cannot promote unlimited installation of powerhouses. We cannot afford to pollute our environment through the pollutants coming out of energy solutions. And minimizing environmental damage is another big aspect when someone works in energy system or works for an energy system with proper energy efficiencies. The government, as you all know, various governments have standardized that not only generation but utilization also should be energy efficient. What does that mean? That means that the appliances or the demand is not uncontrolled. The customer is using appliances which are energy efficient. In mid 20s, people have been using machines which have been consuming power at a low power factor and a poor efficiency. In simple words, to run a small workshop, the demand on system used to be almost 2 times that of the demand today. Obviously, the energy efficiencies were very, very poor at that time, and that is how the systems were poor, the quality of power was poor, the quality of delivery was poor, and we were unable to maintain demand. You would have heard of many interruptions blackouts, shutdowns, load sheddings, so on and so forth, which is not visible today, or we hardly experience such things today. So with this, let us go to the next. What is the situation today in our country? What is the situation today in our country? Can anybody tell me? As a country, India, how much do we generate? How much we consume per capita? Anyway, this particular slide tells you about it. These are recent statistics as early as 30th October 2019. India, or our national grid, has an installed capacity of around 364 gigawatt. 364 gigawatt, of which renewable power plants, including large hydro plants, constitute around 34.86% of total installed capacity. That means one third, almost 120 gigawatt is coming from hydro as well as renewable. Renewable today is around 60 gigawatt. Renewable energy contribution to our grid as on today is around 60 megawatt. Noted? Can I move?
Yes, sir.
Okay. So here I give you just small 2 minutes break before we go ahead with developments in PSD, the second section. Okay. Anybody has any question? Please go ahead. We have around 40 participants, many students. Any student, please come forward. Okay, let me ask one thing. What does 1000 unit per person per year means? In previous slide, we see here, we are using consumption patterns. We are using approximately 1000 kilowatt hour per capita per annum. What does it mean? Okay, the answer is this, that for a population of 135 crore, our annual consumption is 135 crore into 1000 kilowatt hour. Every year, or India need to supply an energy quantity of 135 crore thousand units. Is that clear? If you multiply with total installed capacity, the energy generated, they will be equal to this figure. So let us go to the next part of it. The next part is about developments in power saving conductor devices. What is power electronics? Basically switches. In past, we have been switching on and off using mechanical switches, and the minimum switching time was based on the response of the switch. The switch was operated manually, so it will be the switching time plus the time taken by the person to respond. In nutshell, we can say that we were switching on and off energy in minutes, not in seconds or microseconds, what we do today. That means we had a very, very poor control on switching, which is in turn can be considered that our protections were very, very slow. Right? And all of you must be knowing slow protections means what? Transferring of fault from one end to another end, and finally the total system will be collapsing. Grid may collapse. So those were the days in mid-20s. Now, in 1957, there was a historic development where junctions were converted into a thyristor. Junctions or transistors were known in 1952. They were published in 1952. A small device also made in 1952. 5 years it took for converting that transistor into a thyristor, which can handle some power. Prior to these thyristors, or prior to or before 1957, mercury arc rectifiers and vacuum tube rectifiers were the only devices for converting alternating current into DC. Right? These were bulky devices and they are in museums only now. They had all kind of limitations. You could not have used for higher voltages. You could not have used for higher currents. There were some fixed voltages and currents which were possibly available. Another thing is they are bulky and they also needed some auxiliaries in terms of energizing filaments and things like that. After 1957, till 70, lot of developments took place. And we graduated from simple diodes which were half controlled. That means only positive halves or negative halves of AC cycle could be filtered or rectified. We came to fully controlled thyristors where we could have controlled conduction at any point of 360 degrees of a wave. Right? Further developments are all known to you. Means more and more developments during 1970 to 1985, GTOs, GTRs, power MOSFETs, FETs, BJTs, so many things came into being. And there, with evolution of these new devices, power electronics, more and more control, more and more applications evolved, and the ingress of power electronics was understood. One small observation I would like to put here to the knowledge of all the audiences. During this period, the people who have been at generating stations, they used to kind of complain that new switching devices are introducing a lot of harmonics, switching harmonics into the system, and systems, generating systems need to transfer more of reactive power than active power for that particular reason. And then only the present regulations that harmonic distortion should be limited to 3% was kind of suggested and implemented. So to stop the harmonic contents in power lines, this regulations has been brought during this period, and from there on, any appliance which uses power electronics, was supposed to install a filter by which any harmonics generated in the systems are contained within the system only and are not passed on to the supply side. During 1985 till today, there are more and more developments, IGBTs, power MOSFETs, IGCT, and some devices, integrated devices, where the packs of 4 thyristors, 6 thyristors, or depending on application are available, and device ratings also have been increased from meager volts to hundreds of volts and thousands of current. Let us have a small look at that. This is what it is. This information is slightly older, but still it holds good. The different type of devices and their ratings are tabulated here. Those who wants can note it down, otherwise I'll read it for you. But first of all, let us know what are the different devices available today for us to work with. And each device here listed here has been designed for a specific use by power electronics engineers or electrical and electronics engineers. We have static induction thyristor, followed by static induction transistor, the MOS controlled thyristor, the metal oxide semiconductor field effect transistor MOSFET, bipolar junction transistor. SCRs are very well known, GTs are also very well known, IGBT everybody talks about, IGCT, integrated gate commutated thyristor, also known as GCT. So these are the devices, and if you see the ratings of these devices, whereas walls were only limited to 4 to 500 volts, the vacuum tube valves, diodes now are available for a maximum voltage or peak inverse voltage of 3000 volts, and they can handle currents as high as 3500 amps. Thyristors, even better, they can go to 6000 volt and 3500 amps as the current. That means they can handle power of the order of 20,000 kilowatt. SITH, GTO, Tri-X, BJTs, they are low voltage devices, whereas the first 4 devices are high voltage device and very much required for all power applications where transmission and distribution is concerned. Distribution, we only need low voltage devices, and we can always use devices from 5 to 10. Here also you see that their ratings are also moderate, right? The first 4 devices are for HVDC or for big applications like shunt reactors, switched shunt reactors, or switched capacitors, things like that. So shall we take another break of a minute or two? Because from here we'll start kind of assessing what is the contribution of power electronics in distribution, transmission, generation, and what could be their contribution, future contribution. So we'll just wait for few minutes.
Right, participants, please
Yes.
ask any questions if you have. But before that, please don't forget to unmute your mic.
Yeah, participants, please unmute before you want to talk something or you want to ask something to me. One thing is for sure that introduction and implementation of power electronics has been a boon. It has really saved a lot of difficulties for human or mankind. I'm of the opinion that we need to generate half the power energy today compared to what we have been doing in the past. Every function can be realized using minimum energy, and this has happened only with the support of power electronics. I'll give you more details once we go to different applications. Okay, so we go further. So let
Yes, sir.
us, I have taken few applications in distribution, that is in distribution management 1, 2. So here I'll be discussing with you about illumination, ventilation, heating and cooling, right? When we come to transmission and distribution, which is another big sector where HVDC and FETs are now the style of the day or technology of the day, again supported by power electronics, how much they support. Then we go to generation, and power electronics has a very big role to play in renewable generation. Right? Here we'll talk about some inverters like string inverters and things like that. Then generator 2, when we talk, we'll talk about specific converters for other than solar and their basic requirement, which was just not possible to be met by any other medium. Future we'll talk about energy storage in non-peak hours, that is managing load management or generation management, and then DC grids, which is talk of the day. So these are the applications which we'll be discussing in this section, and let us go to how do we go about this analysis. We are just basically doing an analysis, what was the earlier condition and what is the condition today, and we want to find out or quantify what is the kind of role power electronics has played. So for this we have taken a model wherein what we do, we take a application and we see how much energy we have been consuming earlier and what is the kind of intervention which has been done through power electronics, and after this intervention what is the type of energy is required for this particular application, and the difference in two energies definitely give us a definitely quantifies the role of power electronics in that particular application. So for example, I have a load which is of which consumes W old O. That means the earlier power consumption of that particular equipment was WO and the new consumption is W new. Okay. So saving in what is say W. And if I have similar units in service and N is the number of those units, the multiplication together can give me the total saving in the watts of power required to be generated. Earlier, if I was generating a power equivalent to WO into N, now I need to generate a power which is equivalent of WN into N. And I can find out what is the energy saved per day depending on for how long that particular load has been on. So we take another factor or duty factor. Suppose some load is on for only a part of the time in the day, say 25% of the time. I take it as the number of hours used divided by 24, and that gives me the duty. If something is on for 24 hours, the duty utilization factor is 1. And this is how we can calculate the relief to generating capacity, which is nothing but the first multiplication, that is number of units, because relief in generating capacity has nothing to do with the time of utilization, whereas energy is computed by multiplying this utilization factor, right? Now capex is what? Capex is capital expenditure which is saved by implementation of a device which has been modified and for which the power utilization has reduced and hence the energy requirement is less. When power utilization is reduced, I can always say that I need not spend on any new installation even if there is a new demand, or I have saved the capital expenditure which otherwise would have been necessary for meeting this requirement. And here we have taken a factor which is around 45 million per megawatt. That is the cost of a power generation installation, or this is the average cost of power generation installation, right? That is for installing 1 megawatt power generator, how much we need to spend, which is around 4.5 crore or 45 million Indian rupees. So we'll be using this model and then we'll be analyzing our power electronics contribution in energy efficiency. So we go to the first example, and this will clarify if you had any doubt in previous table. Let us see here. Everybody knows this filament lamp which has been used for almost 100 years. Most of you must be knowing Thomas Alva Edison invented a lamp, incandescent lamp, after he invented DC power, right? And this lamp, once energized, has a resistive element or a filament which is heated and heated to a temperature that it starts radiating, and this radiation is used as illumination finally. Now in this process you see, first of all you energize, you heat element, right? The element goes to a temperature where radiation is possible and you get the light. Most of you would have seen this lamp cover you cannot touch. Once it is on for say 15-20 minutes, the temperature rises. That's an indication that a lot of power is being wasted. It's more like a heater rather than a lamp or a light source. So what we are trying to do is, the efficiency is being compromised. For getting light, we are heating something, dissipating some power, and this is where the energy efficiency has been very poor. When we supply 40 watts to an incandescent lamp, the light output is not more than 2 watts to 3 watts. The equivalent of light which we get, or lumens we get, is not more than 2 or 3 watts. So basically this was a very, very efficient device, and we had nothing to replace it for almost 100 years. Today we have a device, and which all of you know, which is there on the screen. It's a lamp called LED lamp, but it is not only LED lamp. This is LED lamp with a power conditioning unit built in. And this power conditioning unit was possible only in late 20th century. Regions must be better known to you. The element or the light emitting diode or the blue light diode, most of you must be knowing that it has been invented in 1907 itself. 1907. That is almost 113 years back, but it was not utilized. Recognition has come only recently when LED lamps have become way of life, and they became way of life because of this small portion of power electronics which could support it to become a viable light source. And today you see a 50-watt lamp is replaced by, or a 40-watt lamp is replaced by just a 7 to 9-watt lamp, or at the most 12-watt. So having understood this, let us see what is the impact of this, what you call game changer, on the total power system and the energy efficiency. You see the second graph which is given on the right side of this slide, where I have shown there is a blue band and you see the number of units in use in 1990, in millions, I think. 199 million lamps are used or were sold in India in 2019, and they are expecting 210 million units to be sold in next year. That means an average figure of 205 million units is being used in our country. Isn't it alarming? Now let us see a 40-watt lamp. A 40-watt lamp, this 40-watt lamp, which is this one, now consumes only 12 watts. We get a saving of 28 watts on each of this unit. And if we have 205 million units, right, the relief is directly this much, 5.74 gigawatt. That means instead of these 40-watt lamps, if 12-watt lamps are used, we need not generate 5.74 gigawatt of energy. We need not have installation of 5.74 gigawatt of installation. The total energy saved per day is around 1.435 gigawatt hours per day. And if you multiply it with 365, you can think of the figure. Almost 5 to 6,000 gigawatt hours will be saved. So this is the kind of impact of this small addition, which is nothing but power electronics, to render same light to a household which was earlier given by this inefficient device. In other terms, the energy efficiency in illumination has been improved drastically, and the total impact on energy efficiency is around 1.64%. Total impact of this energy consumption reduction is around 1.64% at a base of 350 gigawatt, which is right now the current generating installed capacity for India. So this 1.64% reduction in requirement, it definitely speaks volumes. We'll go further and see more examples Some of you must be thinking is hardly anything, but this is not the only application which is adding to energy efficiency. So we'll go one by one and see. If there are 100 applications like this, whole job is done. But it's not the case. We may not have such kind of roaring examples where this kind of saving is possible. Okay. So in domestic loads, there's another common thing which every Indian household has, and that is nothing but a ceiling fan. Agree with me or not? You'll say yes, most of us have air conditioners. We'll come to air conditioners also, but ceiling fan is something which is remarkable and is definitely used almost like bulbs are used in every house. We generally have a ceiling fan which is a split phase AC single phase motor, has a very poor power factor, and it's an induction motor. The number of fans which are there in use in India, they are in excess of 100 million. Now, if we re-engineer this particular fan, convert the fan into a DC or BLDC drive, and put a power conditioning unit which takes AC power, converts it into DC, and feeds this BLDC machine, we have full control on speed and we have got full control on the output. The kind of savings are claimed today by commercial organizations like Attenberg. They have a model called Gorilla, and they say it needs only 32 VA consumption, and this consumption is totally resistive, that is power factor is 1. Like earlier induction machines, they are highly inductive in nature and power factor is never more than, or it is seldom more than 0.6. So you see the kind of difference it makes when the devices are re-engineered, keeping in mind power electronics available with us. If we do the same analysis here, you see here, we have a saving of around 48 watts per fan. Earlier this fan was consuming 80 watts. Now we need only 32 watts. For a quantity of 100 million and a duty of 0.58, that is 14 hours a day, we have energy saved per day to the tune of 2.74 gigawatt hour, and the relief in generating capacity is around 4.8 gigawatt, which is around 1.37%. With lamps we had 1.64%, and where with fans or ventilation we have a 1.37% impact on energy efficiency. The capex saved for this is around so many million rupees. So with these two small things or very essential things which are there in each and every household, around 3% increase in energy efficiency is possible or has been possible. And that's a great saving. It is almost as if out of 350 gigawatt, you have added 10 gigawatt to the unit. Let us now move on to another very common application, which is in irrigation. We have hundreds of pumps or millions of pumps in this country used by farmers for irrigating farms and fields. Earlier irrigation pumps used to be three-phase induction motors with DOL starters, that is direct online starters. There was no power factor improvement initiative. Later on it was introduced and the consumers have been asked to install capacitor banks at their installations. Some installed, some did not install. And finally, today, looking into the reluctance and non-compliance by customers, it has been shifted to a power electronics solution in the form of soft starters. These starters are nothing but power electronic devices which are of the type of triple VF or variable voltage, variable frequency controllers, and who kind of take care of all pump operations without any difficulty and ensure better life and better efficiency for the machines or pumps. In India, there is no direct figure available from different farmers or utilities. So it's an indirect way of getting this data. We go to different Indian manufacturers and find out how many pumps they manufacture in a year. And you will be surprised to know that in India, we manufacture every year more than 1 million pumps. That means the requirement of soft starter is around 1 million. There are almost 800 pump manufacturers in country, small and big. But the fact is that 1 million pumps are being purchased every year in this country. The population of pumps will be much higher for the reason that there will be some pumps purchased year before and 2 years before and things like that. But working on a 20% utilization of power electronics, we can always consider this 1 million pump as the figure for our computation or in our model for getting the power efficiency. On the right hand side here I have given what type of pumps are used in what type of application other than agriculture, but let us consider all kind of pumps being used in this country. Now here again, energy consumption for each pump varies between 2.5 horsepower to 7.5 horsepower. That is 1815 watts to 5500 watts. This is at a very poor power factor again. Soft starter and VVVF drives with high efficiency SQIM are being implemented, and as I told you, they have been implemented in at least 25% section of this particular demand. Population, that's why we have considered equivalent of 1 million, and energy saved up to 30% is possible with PE support. And this directly comes from the power factor improvement itself. I need not take anything other than that. If I take power factor improvement, that itself makes things much better for us. We also like to point out here that when we are not demanding reactive power, mind it, reactive power occupies line, right? And line capability or capacity to transfer power reduces. But if the demand itself is curtailed, you can think of the benefit what we get out of this. So with a controlled power factor device, we are working, definitely we are much better off, and we need not ask anybody to install capacitors, and we need not look for his or in every individual user's compliance to it. Once a soft starter is there, power factor is no more a concern, and this is the boon, or this is the kind of help extended indirectly by PE or power electronics. So here we can definitely save energy to the tune of 50 gigawatt hour per annum. 50 gigawatt hour per annum. Okay. And this, unfortunately, is not even 1%, it's just 0.4% for us. Let us shift to the second part. Do we have any questions here? Hello?
Any questions from the participants?
Okay, then we'll continue. We have been talking about illumination, we talked about ventilation, we talked about irrigation, and we see that we have got almost 3.4% increase in energy efficiency. We have saved a lot of money in adding installation capacities. Also, we have indirectly reduced the load on transmission line. Since you are demanding 3.4% power less, definitely transmission lines are loaded less by 3.4%. Let us see a different application, which is air conditioning. With time, we see air conditioners hanging out of each and every window in metros, sub-metros, small towns, and now I see even in villages. Most of us who go to Vardhaman college, on the way to Kacharam, we see Narkoda, and you see a lot of air conditioners hanging out of houses in that village. So air conditioners are definitely making way to Indian houses. Earlier air conditioners, they were again simple induction motors, single phase induction motors rated to 2.5 horsepower to 5 horsepower. I am not talking about large systems or block air conditioning systems where things are totally different. We are just considering a large number of air conditioners which are used for general domestic cooling solution. Now, the main current drawn from systems used to be 7 ampere for 1 ton air conditioner, 10 ampere for 1.5 ton air conditioner, and higher for 2 or 2.5 ton air conditioners. So they used to draw somewhere between 1600 to 2500 VA depending on cooling capacity. The population, again from similar market figures if we see today, is around 10 million air conditioners are sold in country as on today, every year. Now, as I told you, the air conditioner, the change today is that we are getting inverter technology. We are getting power factor correction to unity, and we have variable torque depending on the cooling requirement of the system. This was never there. Earlier air conditioners used to be on and they will switch off only when a set temperature is reached. They will start again when the temperature is down and motor will again start. So there used to be hundreds of start on and off. There was poor power factor 0.6, 0.7, and there was no inverter technology. The compressors of those in earlier air conditioners also used to be very inefficient because they were old technology. Now today here out of four things, three things are nothing but controlled by power electronics. So I take it as if the change in this particular technology or whatever energy efficiency is mostly because of power electronics. Let us compute this after. Have you understood? A VVF technology is something like this, where we have got initially the noise filter so that we do not feed any harmonics more than uh, regulated or stipulated or more than permitted. That is 3% total harmonic distortion. We try to convert this AC into DC. We have a power factor correction unit at this point. It's a block in between, and from there we have got an inverter which tries to generate three different pulses and sequences them as required by this DC compressor. It's a switched reluctance motor or similar machine which can be controlled, which doesn't need a sinusoidal AC supply, as I have been mentioning some time back, that we do not need sinusoidal supply anymore for our drives. The inverter can easily control the speed, and by controlling speed we mean that cooling can be controlled. We do not have any further on off control. Here we have got a linear control or proportional control, and the inching or switching on and off operations are totally eliminated. If you set a temperature of 24 degrees Celsius, right, this compressor is driven at a lower speed such that the cool is maintained at 24 degrees without resorting for any further switching on or switching off. The compressor remains on. The power consumption of the compressor reduces because it is working at a low torque requirement, but it tries to maintain the cool, and you have sufficient coolant flow in the system so that temperature is maintained and the losses in the room are maintained equivalent to the cool generated. Okay, so this is totally the operation. Let us see what is the total saving. Now here let me introduce to you, because there are a variety of things here. There is a table at the top where BE star ratings are given. Where BE star ratings are given. That is energy efficiency ratings in India. If we say 1-star rating, the EER is energy efficiency ratio is around 2.3. This energy efficiency ratio is the cooling capacity to the wattage. Okay, that is cooling capacity in watts and power input in watts. As you go down to 5-star rating, you see this ratio is increasing. That means for same watt, you are able to get a desired cooling capacity of 5200 watts. Right? This is for 1.5 ton air conditioner. So if you have 5-star rated inverter type of air conditioner, you spend only 1677 watts. Clear? That means this was possible only because, that means reduction from 2364 watts to 1677 watt was possible with in introducing an inverter, introducing power factor correction, and introducing a controller which can control the temperature as requirement. All three things are nothing but power electronics. Right? There is a small element which I am not talking about, is the compressor. The compressor design also has been changed so that, but that change does not bring much changes here. Like up to 3, you do not have a new design of compressor. The same old design of compressor is working here, but only in 4 and 5-star you have also a new compressor design. Okay, so let us say, take here, we had earlier 2,364 watt being used for a 1.5 ton air conditioner. Today we need 1677 watts. We directly save 687 watt per unit. For each air conditioner, we can have a saving of 687 watt over 10 million. If we take, we are directly reducing a generation requirement of 6.87 gigawatt, which is around 2% at a base of 350 gigawatt. The capex saving is again in billions, right? The total energy consumed in 90 days, the duty cycle here is 0.42, but air conditioners are used only for 90 days during our summer season. So this is again a figure. This figure has to be for annual consumption if you want to see, or annual saving in energy if you want to see. This is the figure, and this is for 90 days base. That means we have assumed that air conditioners are on during summer, which lasts for around 90 days in our country. So this is again a substantial saving in energy, and there is substantial saving in energy efficiency or installed power capacity in the country. Now you see we are inching to now almost 7-8% of total installed capacity has been relieved or spared because of power electronics introduction. That means indirectly, if you see, it is nothing but improvement of energy efficiency. This is nothing but improvement in energy efficiency. Let us move ahead. So domestic we have seen, and we see that we save almost 8 to 9% of energy by implementing power electronics, or the contribution of power electronics or relevance of power electronics in domestic energy efficiency is almost 8 to, or it is greater than 8%, because we have not taken many applications, or we have not taken the applications which have minor contribution, right? So even if we say it's a pessimistic addition, it is 8%. But if you are optimistic, definitely will touch 10% or even go higher than that if all the applications are considered and taken. Let us go to another part. Transmission lines. Transmission lines are power highways or energy highways, right? Energy transferred from generating station to distribution station is through transmission. Any amount of energy, when it flows from a generating station to a load center, it is on wires. The transmission line losses, the capacitive losses are absolutely essential, and nothing can be done without them. In past, T&D losses used to be huge, and people were ashamed to talk about, because not only it was the losses because of poor maintenance of line or poor kind of line structure, or maybe for poor capacities of the line, a substantial part of energy was lost in transmission. Late people have worked, tried to overhaul the lines, add something called switched reactors, capacitors, power factor improvement things, FACT devices, flexible AC transmission devices, to see to it that line losses are contained, line power factors or line impedances are modulated properly, and so on and so forth. Actually, there is a figure called AT&C losses, which is very important for all power trading companies or people who are trading power as a commodity. The AT&C are aggregated technical and commercial losses. So this is of two parts where technical losses and commercial losses both are same. If we consider equal impact of these two parts, every watt saved in ATC helps energy efficiency. Now when I checked it recently, I found that overall all India AT&C losses are 19.9%. 19.9%. This figure was much higher some time back, and in fact some of the electricity boards they are still not able to contain it. Like for Bihar, AT&C losses are 34%. Rajasthan it is 22%. Goa has contained it to just 10%. J&K it is 47%. Jharkhand it is 36%. Our state is also very good. It's around 10.11%. If I take this average 19.19% as a country average and say half of this is resolved because of PE intervention, could be resolved because of PE intervention, we will have a definite contribution to energy efficiency. But it is true that it cannot be brought down to zero. Or any one of you thinks that it can be brought down to zero? Answer is simple no. So we look at world benchmark, and what we found was that South Korea AT&C losses are just 3%. How much? Just 3%. So if we can achieve 3%, which is quite possible for a ideal system or a optimal system which is properly managed, this is possible. And this management has been done by Koreans only with the intervention of power electronics, energy management systems, so on and so forth. This saving of 16% from present 19.9% to 3% could be because of PE intervention. And if half of this is due to technical, we can always say that half of 16, that is 19 minus 3 by 2, that is 8%, definitely can be added to energy efficiency. That means another 8% by introduction of PE in domestic area. We have seen we are nearing 10%, which is already implemented and which is happening. All right, that's why we have additional power availability in the country. That's why we don't have much power cuts now. That's why we have better voltage profile. That's why we are able to get power all the time. Okay, this 8% is in air, and it is possible as time passes, and this will be a contribution to energy efficiency of tomorrow. So you would have understood that the prowess our power electronics has is definitely much sharper, and it definitely can make a big dent in total energy efficiency. Let us also review one more application, that is PE applications in renewable energy generation and distributed generation. Renewable energy is known to you. But you must also be knowing that harnessing renewable energy has been very cumbersome during initial phase. I can give you a simple example. The wind velocity in a windmill is never constant, and hence the speed of a wind generator is never constant. You have to get the power output from a wind generator at different speeds, different frequencies, and different levels. How do you maintain it? How do you maintain a uniform output from a windmill? In initial days, people had put a lot of gearing. They increased low speed to high speed, then connected a generator, and then got the output. But it was improved a bit, but did not improve the way it has been or to a level expected by most of us. We always used to lose energy in this exchange or this conversion process. Today, on the contrary, we can avoid or we are avoiding any kind of generator gear, any kind of gearing, any kind of, we are simply tapping power at any speed, at any frequency, and then storing that power and inverting it using power electronics to a level which is suitable for the grid. So with the introduction of power electronics, harnessing renewable energy has become more convenient and flexible. Not only for wind, it can be applied for tidal, it can be applied for solar, or it can be applied for any other form of renewable energy. So this is a great contribution and this is a great thought by which whatever we have added can now be tapped 100% instead of 20-30% tapped earlier. So that's a great contribution. Not only this, when we talk of renewable energy, we also must talk about the losses, transmission and distribution losses, which are saved by generating renewable energy. Now, this transmission and distribution losses are the losses which we would have incurred because of tapping the power from main grid, and this power would have flown hundreds or thousands of kilometers from the central generating station. The renewable energy generators are placed very close to the load. Say I have a solar power plant, a solar farm or a wind farm in somewhere in Kerala or maybe in Tamil Nadu. The Kerala or Tamil Nadu Discom can directly use this power without incurring much of transmission losses. So there is a difference between the losses in past and transmission and distribution losses today. First of all, I am not tapping 50-60 megawatt of energy. If I consider 60 megawatt installed capacity of renewable today in India, I am not tapping this 60 megawatt from conventional stations. Naturally, proportionate T&D losses have been reduced. So this is indirect saving which we have considered here and which we have taken as an indicator or a contribution from power electronics for energy efficiency. Is that clear? Okay. Let us go to distributed generation. That is another and similar part. All the rooftop generators everywhere in the country, the power requirement to rooftop generators and adding to net energy, grid energy is definitely a reduction of line losses or distribution losses, and definitely it is helping. And it is helping only because of available power electronics by which we are able to interface a rooftop solar to the main distribution system. It's not quantifiable, or we have not quantified in this lecture, but definitely it is supporting our operations. Anyway, this is what I talk to you, so I need not dwell through this. I've already explained to you. Distribution generation is what? It is broadly generation close to the utility. Large areas covered using multiple systems. Faults and blackouts are limited to a system. It principally has both generation and utilization at the same bus. Energy lost in transmission losses is thus converted in DG. Is just conserved in DG. This system could be independent. And this is last figure is only a thing. If you put up a kind of rooftop solar, ROI is very fast. This is how our conventional system works. On the right hand side, central generation is energy intensive and loss prone because energy is from fossil fuel, which is either coal or nuclear. Transmission losses are unavoidable. Energy charge is additionally lost. Energy or charge is additionally lost for capacitive decays, and power factor and phase corrections are challenges in transmission or conventional transmission. Okay, this is further. I need not discuss this. Or let me also talk to you something about domestic grid here today. And domestic grid is basically possible only because of power electronics. Otherwise, not. It was difficult, and it has not been done for last 100 years. I want to bring out a small narrate a small story here. In beginning of 20th century, when electricity was invented, both versions of electricity, DC as well as AC, were patented by two different scientists. You may be knowing them. One was Nikola Tesla, who invented AC, and AC was his marketing strategy, whereas Thomas Alva Edison invented DC and he was promoting DC. As the time would have it, Thomas Alva Edison lost to Nikola Tesla, and we all have been working with AC systems for past 100 years. The only difficulty Thomas Alva Edison had was he did not know how to control DC. The power electronics has given wings to Thomas Alva Edison, and now with the support of power electronics, a DC grid is possible, and this is the most efficient grid as per the study conducted by thousands of scientists and engineers. And absolutely, I feel if not today, another 10 or 15 years, there will be cities where only DC grid is there. Partial DC grids have already, or microgrids have already started functioning, and this is definitely a wonderful energy efficient concept. And another thing which one should understand, AC has a lot of limitations. AC has a lot of limitations. I'll not dwell much on that. Maybe separately we can discuss when it comes to it, or somebody is interested. But DC gives you ample opportunity for flexibility. Today, if you see, 80% of the domestic equipment and drives are DC. All the computers, all the air conditioners, refrigerators, power supplies, they convert AC into DC and then use it because the drives, because the internals, they need DC. So why should we have AC? If we direct have a DC bus, at least one stage or a portion of electronics can be removed. Directly take a DC, modulate it or convert it to the DC level required by the device, which is very simple, and use it. So this is where the utility of DC grid is. There are no losses. There are no losses except for resistive loss. There is no other loss in DC. The other best part in DC is power factor. No talk about power factor. The first and very important part is DC can be stored, whereas just a minute. Sorry, there was some background noise. So is that clear? Why DC grids are important? But it is only when PE is available or power electronics is available, this dream can be realized. Without PE, you cannot have any linking module, which is essential when we work on a DC grid. Here I have shown on the right hand side a small bus, DC bus, and you see whether it is a source or it's a load or it's a storage, we need a interfacing equipment, and this interfacing equipment is only possible with power electronics, not otherwise. So I think with this, let us move on to future scope and trend. What comes to my mind, I am putting here. Energy storage applications is one of the major things which one must think and develop. So my request to all students, faculty, scholars, scientists is that if you are making a career in power electronics, think of energy storage applications. Let me tell you or discuss with you a small application which is called peak demand management, or I'll discuss it maybe in next slides. What is peak demand management? It definitely is a great support to mankind. Another application is energy buffers for e-bus and e-vehicles. DC grid, just now I talked to you and I have discussed about it, but it needs, or you need to develop in future the modules for DC systems and DC fed consumer electronics. Standardization is another part where you don't need to do a lot of modules, and you have all systems which, like in AC today, everything works on 215 volt or 115 volt AC. You are able to complete it, right? You are able to work with that. If you have that international standard, then some of the modules can definitely be reduced. As long as these modules are not standardized, things will be slightly difficult. So we are talking about demand management or future application. You know, this is what is the type of demand which is there in 24 hours. You can see here there's a peak here around 3 o'clock, go down, there's no demand or minimum demand during this period, and further it peaks in the evening and things like that. This is what one of the curves is for night focus, and applications are like this. Okay. Another thing is this. So different loads, they demand power at different places, and together the total demand, you see somewhere here there is lowest demand, there is no demand at all. If you have a power generating capacity here which is able to meet this demand, this peak demand, it is underutilized during this period. It is underutilized during this period. If I am able to think of a solution by which I can pull this particular thing up to the, say this place, or I can use this energy available from the source during this period, I am able to feed to this particular thing without demanding energy from the system. Whatever energy I have stored at this place, I can feed in this particular peak hours. And what will happen with this? The total demand or total installed capacity will be reduced from this level to this level. Now this reduction, if it is 10%, for India it will be a saving of 35 megawatt installed capacity. Or in other terms, for one more year we need not install any new power generating plant. It gives a lot of relief to you. So this is what basically is demand side management for peak demand or peak demand management. And this is possible with power electronics, and we definitely can do this and try to improve energy efficiency. One more thing I would like to tell you, the transmission line at this time is loaded almost to 2 times. Whereas if I keep it here, it is only 1.2 or 1.1 or 1.56 times, 1.2 times, which is definitely another saving in transmission losses. So this is where this application will definitely ease out the load on the present system and will give a new dimension to energy storage and peak management. So this is again, as I told you, interfaces will definitely be required for different, in case you are working for DC grids, right? You need interfacing modules for different, and maybe today people are engaged in designing their individual modules, but if we come together tomorrow and have some standardization, we will be able to do this standardization and improve energy efficiency further. So this is additional kind of future work whether P modified actuators could be thought of. In fact, I do not know whether uh, you are conversant with CD drives and all that. CD drives are not conventional drives. They are definitely P modified drives which are able to give you different speeds, controlled speeds, accurate speeds, very small size, miniature size. Okay, I am almost at the end of the presentation. This is my last one, but one slide. Okay. So let us conclude it this way, that there is a definite impact. The cumulative impact for selected utility is very impressive. Basically, it is an underestimation for limited review. The total impact is definitely much, much higher. The impact is mutual and common to technological innovations as well. P definitely helped in synthesizing the demand optimally. Future developments on energy efficiency cannot be conceived without involvement of PE or PSD. This is a very important thing, and I don't think that in future there will be any devices developed without involvement of PE. The impact is so much that PE is now way of human life. For each and every control, they definitely play a vital role in either miniaturizing or it is reducing total energy demand or increasing energy efficiency. So this is all from my side. I thank you all for your attention and patient listening. So any more questions, comments from anybody are welcome.
Any questions?
हाँ आप कर लो.
No questions? I think no more questions from the participants.
Okay.
It seems.
We can
Right.
close then?
Yes, sir.
We can close.
Yes, sir. So,
Ramesh Babu is okay.
no questions, sir. So, dear participant, this is Dr. Harish speaking on behalf of the organizing committee of the FDP on recent trends in power electronics and energy storage systems. We are at the end of the 5-day FDP. We hope it was useful for most of the participants. The speakers covered various concepts of power electronics from basics to practical issues and applications too. We are very much thankful to our speakers, Dr. Shankar Padpati, Dr. Dastagiri, Dr. Manoranjan Sahu, and Dr. H. Zain sir for such a wonderful lectures. I thank all of them for accepting our request, sparing their valuable time, and sharing their knowledge. We are confident that the content delivered by them would be helpful in your research. I also thank all the participants for patiently listening and their cooperation in smooth conduction of the FDP. We hope there were no technical issues except for few glitches on the first day. Before concluding, I would like to request all the participants to give their valuable feedback through the link shared in WhatsApp group, as it is mandatory for receiving the certificate. Certificates will be mailed to your mail IDs registered on the registration portal, and they will be mailed on Wednesday after receiving feedback forms. The WhatsApp group will be active till all eligible participants receive their certificates. As a confirmation of receipt of certificate, I request the participants to exit from the group once you receive the certificate. Even the videos of all the sessions will be shared to you in due course. That's all. stay home, stay safe, take care. Thank you all.
Yes, sir.
Thank you, sir.